Hello, everybody, and welcome to episode number 49 of Echo Office Hours. Today, we are going to be looking at graceful termination, and there's actually a lot to unpack here. But just as a way of kind of framing the subject, before Kubernetes 1.20, if you wanted to, say, drain a node or cordon a node or anything else like that, there were some challenges. You would have to go through some very specific processes to accomplish a method by which the nodes on that, the pods on that node would actually be removed gracefully from the services that have been defined. Instead, what would happen is that you would, if you, before 1.20, if you were to just cordon a node, drain a node, then what happens is any pods that are on that node would continue to participate in the services defined within the cluster. And that could cause some interesting behavior for applications that you might have deployed, in that the applications would continue to be chosen as a healthy backends for those internal load balancing mechanisms. And that means that if you were going to access a service from within Kubernetes, from outside the cluster, or even within the cluster, even if the pods are hosted on a node that has been marked for termination or marked for draining, those pods would continue to be serviced. They would still get new connections, regardless of whether they should be considered healthy. So that's kind of the stuff that we're going to dig into. There's a couple different pieces here. There's a piece about the node itself, and there's also a piece about the way that pods and endpoint slices work in 1.22. And we're going to kind of dig into all of that. So that's my plan. As usual, if you are, even if you're here for the first time, if you look down here at the bottom right-hand side of the screen, it says show notes. And if you go to hackmd.io/echo live, you'll see all of the show notes that are available. In fact, I think I might have forgot to do one thing here. So let me go ahead and do this. Yeah, I forgot to do this. 049. Save. Okay. So that means that if you go to hackmd.io/echo live, you're going to be able to see this particular hackmd, and that hackmd will be available to you to see the notes that I'm going through, and also put any links up that you think might be relevant for the show. It also has a handy link for the YouTube session here, but I'm not going to play that because that would probably end up giving us weird feedback or something. Also, if you are a part of the stream, if you're watching this live, please let me know. It's always nice to know that people are out there live. And so if you are live, just go ahead and throw a comment in there, say who you are and where you're from. And it's always nice to see that. So if you're listening to this live or watching us, let us know. Hey, Mr. Christopher, good to see you. Christopher sending us some good vibes. All right, so headlines. We got a new Echo newsletter. So if you're interested in the Echo newsletter, you can click on that link. This is episode 8 of the Echo newsletter. And we're usually trying to keep interesting things that are happening within the eBPF space, and like different projects that are coming along, kind of making people aware of what sorts of things are happening in this space here. So if you're interested in kind of following along, or if you want to subscribe, if you were to click on that link down at the bottom, I believe there is a subscription link. Oh, it says unsubscribe, but you can click on manage preferences, or there we go. You can do a sign up today thing right here on the bottom. Okay. You can also follow the Cilium Twitter handle, and whenever there's a new episode, the Cilium Twitter handle will announce it, and that's another way to actually get a hold of this news. So Christopher, who's actually in the chat, and Dan Borkman, this year at KubeCon, actually did a whole presentation on this BBR-based congestion control for Kubernetes pods. Using real-world adaptive video streaming use case, they will compare two different network conditions, comparing BBR-based congestion control to the Linux default cubic for pods. Now, this was an interesting talk, and it was a really interesting presentation because it got into, like one of the topics that I think is always pretty fascinating to me, which is that, kind of gets into, as we move toward this container orchestration scenario, right, as we adopt Kubernetes and a lot of the other container orchestration models that are out there, the question becomes like, is the Linux kernel like keeping up? Like, are all of the primitives that the Linux kernel exposes able to be used even within those namespaces that we create when we start going the container path? And in some cases, the answer is no, which is interesting. So, like, for example, in this particular case, the BBI, congestion control was not actually available within pods yet, right? Instead, you were stuck with whatever the default was, which at the time was cubic. And this is one of the things that they cover in this presentation. Thanks to some of the work done by some of my fellow employees here at Isovalent, that's actually changed. And so now you can actually make use of BBR-based congestion control, which is a better congestion control for things like video streaming and a lot of the other use cases that are out there. So if you're interested in that topic and understanding how and why it works, definitely check out that article. My friend Leo Dido put out a thing called Traffico, which is an interesting one. It's kind of taking the approach of some of the other CNI plugins that I've seen, in which you'd be able to basically chain this to be able to implement traffic control leveraging TC. So this is leveraging eBPF. And the idea is that you would have whatever CNI you're going to have, but you also want to have some control over traffic control. And this is a plugin that you can chain in your existing CNI model inside of your cluster that would allow you to do that. This is actually one of the things that Cilium does natively. But if you're using a CNI that isn't Cilium, then that's another option to kind of explore. We have tracing TLS traffic eBPF style. I've been in a couple of conversations this week that kind of get into this piece of it, especially as there is apparently a new version of OpenSSL coming along pretty soon that will encrypt a lot more of the header information than was previously encrypted. So like today, if you try to establish a connection between, say, your web browser and some HTTPS website like Google or one of your secure financial sites or whatever, there is some unencrypted data that is actually a part of the initial transaction, including what's called the SNI, or the server name indicator. And that is used frequently to determine, okay, well, when it lands on a web server on the other side, or a load balancer or anything else like that, that SNI field is used to direct your traffic toward the correct backend or the correct service. And for the longest time, that SNI information was unencrypted. So you could actually make L4-based decisions without doing any encryption or anything else like that, based solely on the SNI that was unencrypted. And apparently, and I haven't dug into this too far, but apparently there's now an opportunity to encrypt even that data. And so it'll be kind of an interesting thing how that will actually pan out. Like, thinking out loud, I'm struggling with how it seems like you would have to terminate the load balancer with some kind of a wildcard certificate, and then decrypt the traffic based on that initial connection, determine what the actual SNI is, make a different decision about where to send that traffic now that you've actually terminated it on wildcard. So overall, that doesn't make a ton of sense to me, but it has been brought up a couple times. And so, yeah, I might dig a little further into what's happening there. But what this article is about is how do we actually trace TLS traffic leveraging eBPF? So, interesting stuff. I believe they're probably going to insert dramatic music. I love it. eBPF, the dark knowledge. Mm-hmm. User space probes. What are we looking at? So talking about the libSSL, which is going to handle your encryption. Ah, nice. Okay. So leveraging TLS to do this piece of it. Interestingly, I'm not seeing. So basically, they're using a uprobe to hook before the encryption happens in user space, which is interesting, because some of the other stuff that's happening in this space is the ability to move encryption up to the kernel, which is called KTLS, or kernel TLS. And if you do move it up to kernel, then another thing that we could do with eBPF would be to defer the encryption to after we have had a chance to inspect the traffic. And that would basically take this piece where you're doing the SSL encryption, and the encryption would then happen up in the kernel instead of in user space, which would be which could increase the efficiency of that encryption piece of it, but also gives us the ability to perhaps inspect the headers and the SNI and that kind of stuff before things are encrypted. That's where I thought this article was going to go, but that's actually not where it ended up going. Interesting stuff. We also have tastes great, less filling, high performance, and accurate training data collection for self-driving database management systems. eBPF is making databases more manageable. Excuse me. Have the tail end of the Omicron cough. I actually ended up catching COVID-19 while I was in Spain and isolating there for 10 days. And so it actually wasn't bad. I was triple vaccinated, so I got over it pretty quickly. The problem is that with the Omicron thing, if you get it, you end up with this like dry cough that keeps going, which is fine as long as you don't say anything. But as soon as you start talking, like we're doing right now, it makes you cough. So hear me cough, that's what's up. Good, interesting article about bypassing eBPF-based security enforcement tools. And Pixie, using an X-ray machine for Kubernetes traffic. Learn how Pixie uses eBPF for observability. And in the ecosystem, we have a few things. Been a great article. eBPF sidecars and the future of service mesh. The conversation's getting pretty interesting. There's lots of people who have a lot of feedback on it. Yeah, if only we didn't talk daily. That would be something. Symbiote, a new, nearly impossible to detect Linux threat. I actually just saw this one. Pretty interesting in the eBPF section. I'm not going to dig into it too far. There's also a new version of Inspector Gadget out by the fine folks at Kinvoke, so that should be interesting. Big updates to this eBPF-based tool from Kinvoke, especially around user experience and making it easier to discover new tools. Managing distributed applications in Kubernetes using Cilium, Istio, and Helm and Operator for deployment. That might be an interesting one to kind of dig into in one of our sessions. We have Contain IQ with Matthew Leonard and Cilium CNI and SKS. Exascale SKS now supports Cilium. At this point, I'm not sure if there are many clouds that don't. Seems like a lot of them do, which is pretty exciting. I was actually just looking at this article, and I think I might try to reproduce this here on office hours. So I think I might reach out to Deck here and see if he'd be interested in kind of pursuing this internally. But what they're doing here is they're basically bringing up a cluster in their home environment that can support a dual stack arrangement. And I know that some of that stuff is supported in kind. And even if it weren't, I have a way of actually bringing up kind of a similar environment in Vagrant. So it'd be kind of an interesting one to look into. But yeah, this is a really good article that gets really into some good detail about how to manage dual stack, IPv4, IPv6 dual stack. Right. And so this is the install command for Cilium, basically installing a IPv4 pod CIDR list. That's the IPv4 address space that will be used. And then the IPv4 or IPv6 pod CIDR list, which is the IPv6 CIDR that will be used for pods. And then the different mask size. These mask sizes are about how many of those IP addresses are allocated to each node, so that they can then further allocate them to pods. BPF masquerade for true. Disabling IPv6 natting because we can use a routed subnet. That's actually pretty neat. Yeah, and he gets right down into the detail. Starts looking at load balancers. I think he's actually using, isn't it Metal LB for that? Yeah, he's using Metal LB. It's not widely advertised or documented, but it does fully support IPv6. So in his case, he's using Metal LB for the load balancing, whether for IPv4 or IPv6. And he's using the layer 2 mechanism, which means that he's actually, ARPing out from the node where a service exists on from a single node where that service exists, not all of them. Very cool. And then he's got a whole test scenario. So I was thinking about doing this one live on office hours, and I think I might dig in and do it. It's a fun one. And IPv6 is kind of, I think, a pretty interesting piece to dig into. So this blog also looks really interesting, yoloops.net. Definitely check it out. Hey, Raphael, good to see you. All right. The events. There's a creating a community with Cilium. See how the Cilium community was built with Liz and Thomas on June 15. This was an event hosted by Equinix Metal, and then eBPF at Open Source Summit. Multiple talks about including building an eBPF Swiss Army knife, powering observability with simple shareable eBPF programs. Lots of really good stuff in here. And that OSS Summit is coming right up in Austin. I think it's June 21st and 22nd. So definitely check out those talks. Also, episode 48 or 47 was the KubeCon EU wrap-up. And then 48, we actually did a whole thing on Pixie. So if you're interested in Pixie, you can definitely check out the previous episode. And then, talking about the stuff that's coming up. The next Plumbers Conference is coming up. Lots of eBPF stuff happens there. Yeah, so that's the news of the week. Let's keep going. Let's dig into it a bit further. Oh, typo. Boop. There's only one P in points. X. All right. So there's a couple different pieces to this, like I said, and we're going to kind of explore them and play with them and look into them live here. So first thing I wanted to show was kind of talking about how pieces and parts of this work. So looking into this is actually the documentation for the endpoint slices that are now available within Kubernetes. Endpoint slices, I think, were introduced some time ago, but they went stable in version 1.21. And that means that the API for endpoint slices is considered stable. However, in 120, we did introduce an alpha feature, or we started extending some of the endpoint slice information to give us hints or information about what's actually happening with endpoints and to be able to make better decisions about what to do with traffic associated with those endpoints. Now, previously, again, that was the initial implementation of endpoints within Kubernetes. It just considered all things healthy unless those things didn't pass a readiness check. And even if they didn't pass a readiness check, it might take a little while for things to converge in such a way that the unready pods would then be removed from the cluster. But now we have a new feature that was introduced. Here we go. There was a new feature that was introduced in 1.20 in alpha. And actually, I just realized that this is a documentation bug. We probably should try and fix this. But the endpoint, the terminating field in endpoint slices is actually now on by default and was introduced. It went to beta in version 1.22. But it looks like in the docs, it still says feature state alpha in 1.20, and that you would have to enable a particular feature flag. But that is no longer true. Interesting. Okay, so that's probably that's a doc bug, and maybe we'll get to fixing that today in our session. But yeah, this should say feature state Kubernetes v1.22 beta and on by default. This is the KEP for it. If you're curious about digging into what the motivation is here, the motivation is to provide a mechanism to track whether an endpoint is terminating by only watching the endpoint slice API. The consumption of the new API field is out of scope for this KEP, but kind of gets into what's happening here. A consumer of the endpoint slice API, for example, kubeproxy, or in our case, Cilium, may want to know which endpoints are terminating without having to watch the pods directly for scalability reasons. The other benefit of this is that, if an endpoint is marked terminating, then we can make better decisions about what to do with the traffic. So, for example, if an endpoint is marked terminating, then we could pull it out of the running for any existing traffic, and we can continue to allow for the traffic that is actually already terminating on that node or on that pod or on that endpoint to continue, but that we wouldn't send any new traffic to it. Previously, we kind of had, we were watching the pod endpoint, the pod API, and that might be, it would take a little while for things to converge because, how that would work. So one example would be the IPVS proxyer, which should set the weight of an endpoint to 0 during termination, and finally remove the real server when the endpoint is removed. Without knowing when a pod is done terminating, the IPVS proxy makes a best effort guess at when the pod is terminated by looking at the connection tracking table. Some really good detail around what's happening here. So I know that this field is present in versions of Kubernetes forward of 1.22, and I think I can even identify. In fact, let's see, Twitter. That's actually how I noticed this. Yeah, there we go. So I was looking at the docs, and I was like, oh, I have to turn on this feature. But then I also noticed that my friend Andrew Sykim, who is on paternity leave, so congratulations to Andrew and the brand new baby in the Sykim fam, which is really super awesome. Said, starting in Kubernetes version 1.22, the endpoint slice API will include PON endpoints that are terminating. And that means that in 1.22, it went to beta and became a default. And you can actually see that if you click through to the issue. This has been merged. We can look at the commits. And you can see if you click on any commit in the Kubernetes codebase, you can see where that commit sits against the tag set, right? So in this case, it was merged in v122 0 RC0. And then, any subsequent tag after that, of course, will also have it, right? And so, and then the other piece that's interesting is this line right here, which is indicating that on July 8th, 2021, when this merged, it was setting the default to true, and then the feature gate is now in beta. And this is the feature gate, endpoint slice terminating condition. So prior to version 1.22, if you want to play with this, you would actually have to set that feature gate value. But now it's actually by default true in any version of Kubernetes forward of 1.22. That's why I was saying it's a doc bug, because I'm pretty sure that should already be there. All right. We talked about this one. And let's talk about how this integrates with Cilium. This is a great little blog post. This was our blog post for version 1.11 when it was released, and it talks about graceful termination of the backend. And so the idea, I think this is actually supposed to be a GIF, but doesn't seem to be GIFing. But the idea is that you would, I wonder why. Let's see. If I open it in a new window, does it still GIF? Huh. Is it not a GIF? Definitely a WebP. Interesting. I'll figure out what's happening there on the blog. That seems odd. That should be doing stuff. Anyway, Kubernetes can terminate a service endpoint pod for a number of reasons, like a rolling update, a scale down, initiated deletion. In such cases, it's important that the active service connections to the pod are gracefully terminated, giving the application time to finish requests in order to minimize disruption. Abrupt connection terminations can lead to data loss or delay application recovery. So to talking about that a little bit more, what that means is your consumer on the back end here, right? Your application is actually trying to access multiple backends, right? Like we were talking about before when we first started this episode. When this client side tries to make connections to a service and is balanced across multiple backends, that part just works fine, right? That's a regular Kubernetes service kind of a model. And there's some decision-making processes. So especially if you're leveraging Cilium, when that application tries to make a connection to the load balancer, Cilium will actually determine which backend to connect to. And if you're using kubeproxyless mode, then Cilium is the only thing that will make that decision, right? And so basically, if you're working in kubeproxy mode, then the traffic, when your client side tries to access the server, it's going to access that service by cluster IP, and then Cilium will make a decision about which healthy endpoint to send the traffic to, and it's going to make that decision based on parsing the endpoint slice data for that given service, right? So it's going to see which pods are in a ready state. It's going to see or in a serving state. It's also going to see which endpoints are in a terminating state, and if it sees any in a terminating state, it's going to remove them from the running. So if I were to look at the load balancer as defined within Cilium, I'd be able to see that those endpoints are no longer in the list because they have been marked a terminating state. But if they're in a serving state, then those endpoints are in the list and could be considered for sending new traffic. Now, this actually only talks about what we've talked about here is only going to relate to like a new connection coming from your client side, going to the server side using a cluster IP. Which healthy backend is going to be considered is actually a function of whether that endpoint is terminating in a terminating state or in a serving state. It doesn't talk about the other piece of the puzzle here, which we've talked about a little bit in the opening paragraph here, which is that you have the part of the puzzle of like what endpoints are considered, but you also have the part of the puzzle of any existing connections that you have between that client side and the serving side should remain working until that connection is done, right? Until that connection has been terminated. And there are a number of different ways to actually determine that that's the case, right? Like you could actually be looking at contract on the inside of the network namespace. You could just, wait for a period of time. You can do a number of different things to actually control how much time to allow a backend that is in terminating to drain before you delete it, right? But there's lots of stuff that you can do kind of here on the backend piece to make sure that you're not going to just yank the plug, as it were. You can kind of give it more time to terminate. There's a grace period, seconds, how long it's going to wait between sending a sig term and sending a sig kill. There's lots of functionality there that you can actually control. But that's two parts of the puzzle. First part, when the load balancer is making a decision, which endpoints are considered. If we see via the endpoint slice API that particular endpoints are terminating, then we should remove them from consideration for the endpoint. The second part is existing traffic should continue to work to that backend endpoint. We shouldn't just, ungracefully drop traffic to that endpoint. We should allow for that traffic to continue until such time as the application has had a chance to drain. So two parts to the puzzle. So Cilium agent listens to the endpoint updates via the endpoint slice API. That's what we talked about before. And when a service endpoint is terminated, Kubernetes sets the terminating state for the endpoint. Cilium agent then removes the data path state for that endpoint such that the endpoint is not selected for new requests, but existing service connections that this endpoint is servicing can be terminated within a user-defined grace period. In parallel, Kubernetes instructs container runtimes to send the sig term signal. That means that basically as soon as it receives some signal, and actually this may happen out of order, right? That sig term might have happened first because you have marked for that, you've marked that pod for deletion. And as soon as you mark that pod for deletion, you're going to see the sig term show up on the pod. And it waits for the termination grace period. The container applications then initiate graceful termination for active connections, closing TCP sockets, hoping that your application will understand sig term and that when it sees a sig term, it's going to do the right thing. It's going to start shutting things down, but it's not going to immediately exit, right? And there's actually some kind of interesting caveats there too, right? Like if you sig term a bash process, that's it, you're done. Everything is done, But if you sig term an application that understands sig term or is trapping on sig term and will take some action, then that's a different thing, right? Like Nginx, for example, will actually start shutting things down in the TCP sockets and that kind of thing. Kubernetes finally, after the period of the graceful termination, will send a sig kill, and that can't be trapped. That just means that get out of the pool. It's done. It's time to terminate this application. It doesn't particularly care at that point. When the sig kill is sent, any existing connections are then terminated directly, right? So your plan, your goal here is to make sure that you have enough time between sig term and sig kill to allow for the graceful termination of connections. And that can be an active process. Like you can write into your code that when you see a sig term, you got to drain those connections and get about it and set some period of timeout by which you would accomplish this. Or you can just set like a regular sleep or some such like that and allow for the application to kind of just regularly terminate it because it's not receiving new connections. So depending on how well you understand your application, or how deep you want to go down that rabbit hole of managing the time between sigterm and sigkill, you have a little bit more capability there. At this time, so once the sigkill is sent, once the grace period ends, at this time the agent also receives a delete event for the endpoint, because effectively the kubelet has marked the pod for deletion, and then it completely removes the endpoint's data path state. However, if the application pod exits before the graceful termination period ends, Kubernetes will send the delete event immediately, regardless of grace period. So an example of that might be, you have set a graceful termination period of seconds to like 90 seconds, right? And then you do a deletion on a pod. So you said kubectl delete pod. Now that marks the pod for deletion. That also marks the endpoint in the service for terminating. So now we're not going to send any new traffic to that pod that has been marked for deletion. You have that 90 seconds that is going to between sigterm and sigkill. As long as your application doesn't immediately terminate when it sees a sigterm, then any existing connections to that pod will continue to operate. At the end of that 90 seconds, the kubelet is going to send a sigkill, and the kubelet is also going to mark that pod, effectively moving forward into a deleting state or terminating state. And so we'll see the terminating state for the pod actually show up in the API. As soon as that terminating state, as soon as that sigkill happens, then the kubelet says, okay, I'm going to start deleting this pod. It goes about sending the deletion event, and the pod gets deleted, and that's what notifies the Cilium agent, or the CNI in this case, that the pod is no longer, right, that it needs to be deleted. And so that would be just another one of the API calls that the kubelet makes to the CNI, saying pod deletion, here it is. And then that is actually how we know from the agent perspective that we need to pull out the rest of the data path because the pod has been deleted. Interesting stuff. All right. So that's what we got so far. I am also going to talk about node graceful shutdown, but let's do that after we have kind of played with things a little bit. So let's get going here. I have 4 nodes. They're in a not ready state. And they're in a not ready state because I actually haven't configured them with any CNI yet. We're going to do that here live in this cluster, in this configuration. Oh, there's one more thing I wanted to show. One more thing I wanted to show you on this piece of it, which is the Cilium docs. So this is the docs that we have for graceful termination and how it's supported within Cilium. So Cilium's eBPF kube proxy replacement supports graceful termination of service endpoint pods, as we talked about in the blog, right? And the idea is that this feature requires at least Kubernetes version 1.20 and the feature gate endpoint slice terminating condition needs to be enabled. By default, the Cilium agent then detects such terminating pod state. If needed, the feature can be disabled with the configuration enable K8's terminating endpoint. So what that means to us is that this feature is on by default, or this feature, when the agent starts up, it's going to evaluate whether the endpoint slice terminating condition feature flag is set to true or false, right? Prior to 1.22, it was set to false, and you would have to enable it explicitly because it was an alpha feature. Now it's in beta, and it's enabled by default, which means that when the agent starts up, it should see that the graceful termination feature is in a healthy state, and we should be able to see that feature inside of Cilium. So let's go ahead and get things deployed here. So like I said, I've got a cluster deployed. I don't have kube proxy running. If I do kubectl get pods -aw, I can see I don't have kube proxy running. I have my 4 nodes. I have a control plane node, a couple worker nodes. And core DNS is not started up, and that's because it's not actually There's no CNI deployed, so let's go ahead and kick this off here. So I'm going to do Cilium install help. And my goal here is actually going to be to turn this kubeproxy feature into strict. So let's go ahead and do that first. Kubeproxy replacement strict. And if I do that, then I also have to set some other interesting information, right? So for me to turn on kubeproxy replacement, I have to tell Cilium how to access the API server, right? And so I'm going to hit Control C here, and I'm going to do kubectl config show. View, sorry. And we can see that the URL that I'm using to interact with the cluster is api.c1.k8.work. Okay, and that's a load balancer that I have configured in front of the cluster. Right, so api.c1.k8.work is actually going to an HA proxy instance that will disperse this traffic across all of the control plane nodes. But there's only just the one control plane node, so the load balancer is kind of a load balancer in name only at the moment. But we need to set this value, and we're going to talk about a little bit about why, right? So if we're leveraging Cilium in kubeproxy replacement mode, that means that we have to tell Cilium how to talk to the API server so that Cilium can effectively handle the part of the mechanism that is kubeproxy. And you do a similar thing with kubeproxy itself, right? So when you're configuring kubeproxy in a regular Kubernetes cluster, kubeproxy has a kubeconfig, and that kubeconfig configures kubeproxy in such a way that it knows how to go and interact with the Kubernetes API. The reason this is important, and this is kind of an interesting chicken and egg scenario, if you don't tell kubeproxy how to go talk to the API server, how does everything else within your cluster that's going to talk to the API server talk to it? Like, how does, say you're going to create like, a silly little kubectl command that would, I don't know, do an inventory check, right? It's going to check all the pods running in a given namespace, or maybe it's going to automatically approve CSRs. That's another good example. So I create a cron job. That cron job is a kubectl command. It's going to use its service account to authenticate to the Kubernetes API and automatically approve CSRs. Within Kubernetes, the construct for this is actually this internal load balancer mechanism, this internal Kubernetes service. I do kubectl get svc in the default namespace. I can see that there is this Kubernetes service that's been defined. And it has a cluster IP, which is the first IP address in the service-sided range for that cluster. So this is an interesting one because it means that inside the cluster, you can actually access the Kubernetes API directly at kubernetes.default.svc. And you can use your service account to authenticate to it. So depending on what role you associated with your service account, you can actually, grant any kind of a role you want to that service account, and that service account will be able to authenticate to the internal representation of the Kubernetes API server. This internal representation, this cluster IP mechanism, is actually implemented by whatever's going to handle kubeproxy. So if you have kubeproxy running, that means that, and you're using like the IP tables mode, for example, then that means on every node where kubeproxy runs, it's going to inject some IP tables rules that will implement this this service, right? So anytime, and you're going to see those IP tables rules are going to say stuff like, from the pod side of range, if the destination is 1096.0.1, disperse that traffic across the known endpoints for this particular service. Let's do kubectl describe svc Kubernetes. We can see like how that would be wired up, right? So if the IP tables rule would be like, if your destination is 1096.0.1, then, and the destination port is port 443, then NAT that traffic, right? Send that traffic instead to 192.168.201.21 on port 6443. Within your cluster, that's how it works. Kubeproxy needs to know before kubeproxy is up how to implement this stuff. That means it needs to talk to the API server before there is any implementation of kubeproxy. Obviously, that's the chicken and egg part, right? The way that it does that is that on the node itself, actually, let's see. I bet you it's there. Let's take a look. SSH 01 Kubernetes. Oh no, it doesn't. Yeah, neat. So it doesn't actually generate it if you're not using it. And I've told it not to deploy kubeproxy, so it doesn't get one. But I think if I go here, nodes. Yeah, okay. So I have a kubeproxy. I have another cluster that's been brought up just leveraging kind. So let's just jump into one of those real quick. Docker exec ti-n kind control plane bash. Let's see, Kubernetes. This is all assuming kubeadm. So manifests cat. W. Proxy is running. This manifests. So those are the static pods. Wonder where, so kubectl describe deployment, kube-n, actually daemon set, -n, kube system, kube. Config map, -n, kube system, kube. There we go. Okay, so you can see that the way kubeproxy is configured in this scenario, here's the configuration for it, right? It's in a config map inside of kubeconfig. And the kubeconfig that is being populated for it is talking to kind control plane 6443. This is the same configuration that we're talking about, right? We need to actually pass something to the kubeconfig that allows for kubeproxy to interact with the API server directly. And that's how that piece is working. So we got to do a similar thing for Cilium, which is the point. So let's move into C1 here. So I'm going to take a look at the docs here real quick. And I believe we're kind of already in the kubeproxy replacement mode. So there we go. So these are the values that I have to set to actually make use of this functionality, right? Where it says set Kubernetes service host, and then we're going to replace it with our server IP or FQDN, and then service port, we're going to replace that with our port. So let's go ahead and do that. Now I am going to use the Cilium command line for this. Because it has a new feature. It's called Helm Set, which is actually pretty neat. So kubeproxy replacement strict Helm Set. Okay, service port or service server IP, and that is api.c1.kades.work. Helm Set Kades service port. It defaults to 6443, but we're going to go with it anyway. I want to see, I think there is a Okay. So in theory, that should be enough to get us where we're going. Let's try it out, see what happens. So Cilium install, keep proxy replacement strict. A couple of different Helm sets. Helm set can specify multiple or separate values with commas. Ah, okay. Should have read that before. Wink. Okay. So that should be enough to get us there. Let's give it a try. So we can see that the values have been parsed. We can see them in here. So we're in kube proxy replacement strict. We see the K8 service host and the K8 service port is being set. Hey, it looks like things are working along. Cilium's coming up. Good stuff. Operators running. Cilium is now running, so kubectl get pods-aw. Waiting for CorDNS to pick it up. Oh, there it goes. Alrighty. Everybody happy? Cool. So that means now that we have that implemented, right, then we should actually be able to do stuff like, say, SSH CP01. We should be able to do curl HTTPS 1090. Oh, you know what I didn't do? How this will work out? Get pods-aw. Wide. Yeah, I went with the default pod CIDR, which is the 10.0 range, which probably is going to be fine, but like it's an interesting thing. Okay, so let's see. What I wanted to see was kubectl. So inside of here, if I do kubectl get svc in the default namespace, I have my 1096.01. I'm going to SSH into cp01.c1 here, which is my control plane node. And I'm going to curl it. 1096.01. Colon 443. This is going to be testing that service. And I'm wondering, it may or may not work, because I'm not sure if we have to have certain host-enabled services turned on, but let's give it a try. Health Z V. Yes. Oh, is it -I? Is that what I'm looking for? Insecure. And then that endpoint. Hey, it works. Okay. You can see down here at the bottom, I got an OK, right? And that means that I'm actually just interacting with that endpoint directly. And we can see the API server is responding, and we're getting an OK for health. And that means that the service is working, right? I'm actually able to see that. And if I were to do sudo IP tables, save grep 1096.01, we do not have it still looks pretty IP tablesy to me. It still looks like pretty kubeproxy to me, which is actually pretty interesting. Sure. Wonder if that's an artifact of not having wiped out the cluster before I actually did this reinstall. Because like those IP tables rules should definitely not be there. It's kind of interesting. Yeah. And these are actually created by kubeproxy. So you know what? Let's just use kubeproxy to clean them up. So Docker images, start get all images, curl. So let's do this. Curl kill.kh.io. V124 2. Okay. I am going to show you a cool website. Download Kubernetes.com. Download Kubernetes.com actually gives you the short links to download all the bits and pieces of Kubernetes. And you can see the checksum for them. You can also see the short link to pull it down, right? So let's see which actually version let's see what version of Kubernetes I'm using again, because I kind of forgot. So export, let's do up here because we're already authenticated. So the Kubernetes kubectl version. We're running on the cluster side 124.1, right? And so we're going to go ahead and grab 124.1. So let's go over here and we'll grab the kubeproxy binary. This will download the binary directly, which is actually pretty neat. And let's just go ahead and do that. Curl -lo, paste that line in there. There is our kubeproxy. We'll do change mod plus x kubeproxy. And then we'll do kubeproxy, actually sudo kubeproxy cleanup. It's complaining about IP set, but that should be okay. So now if I do IP tables save sudo, I don't see any of the service stuff. That's all been pulled out because what I've done here is I've made kubeproxy kind of clean up after itself, which is a handy trick for kubeproxy. And I think what happened was that when I was running this test before, I was trying to deploy Kubernetes without kubeproxy, but I didn't actually wipe out the IP tables rules in between attempts. And so I ended up in that state. So if I do my sudo IP tables save command now, I can see it doesn't work. But let's see if this still works, because this might not actually work now. Oh, it still does. Nope, wrong one. Still works. Yay. So now we know that this is working because of Cilium, not because of the kubeproxy IP tables rules that are still sitting in the cluster. Interesting stuff. couple other things we want to do here. So let's do kubectl get pod -n kube system, and we'll look at the load balancer implementation of Cilium. O wide grep cp01. So there is our Cilium agent running on that node. So I'm going to go ahead and exec in there. Kube system, Cilium 4, bash. eBPF lb list. Oh, excuse me. So in here, you can see this is the implementation of the Kubernetes default service, right? And it's saying if your destination, just like we talked about in the IP tables rules, if your destination is 1096.0.1.443, then I want to send that traffic to the one healthy backend that I know about, which is 192.168.201.21.6443. And that is how that part is working right now. Right. Now for some fun stuff. I mean, this was already pretty fun, but you know. Oh, you know what? I probably should do that cleanup thing on the other nodes. Yeah, probably so. SCP, CP01, C1. C, and we'll do that. We'll move that over to worker 01.C1. Wow, and Meg. Interesting. Wonder why that's so slow. Probably because it is. Yeah, I don't know why that's so slow. That's interesting. Worker 01.C1. Curl minus LO. Hit split vertically again real quick, just so I don't have to like remember everything. Copy SSH worker 01.C1 curl minus LO. And 3 for worker 1.3. And yeah, there we go. SSH W sudo cube plus X cube proxy. We do that. Let's make sure this is going to work. So we'll do sudo tables save wc -l. How many rules are on each node, and then we'll do sudo q proxy cleanup. Blah blah. All right, so we got all that figured out. Let's keep going. Next thing we want to do is we want to create some stuff. So I'm going to do kubectl create deployment echo image equals. So we'll just use that inanimate echo server. Inanimate echo server replicas 30. Port 8080. starting up. Ooh, sorry. So now we have our pods running. So I'm going to do kubectl expose deployment echo kubectl get SBC endpoint slice YAML. Watch it, and we'll do a grep, egrep. Actually, let's do the egrep. Well, let's just do a -l YAML first. So this is what the endpoint slice looks like. And there's a bunch of different endpoints defined in here, and they all have this set of conditions, and they are all associated with node names, and they all have a name as well. So here's what I'm going to do. I'm going to do -watch, and I'm going to do an egrep, and the fields I'm interested in seeing are these. So I'm looking for name. I'm looking for terminating. I'm looking for name, terminating, and node name. Okay. So we can see this is like, this is a very similar thing to what the Cilium agent is doing here, right? So it's actually watching for this endpoint slice API, and it sees all of these endpoints behind it. So let's go ahead and leave that there. I'm going to split this vertically. We can have our watching all of that. And then up here, actually, I want to split this vertically too. No, it didn't work. Let's go ahead and grab this real quick. We'll paste it over there. Okay, there we go. Clear. Control D. So now I'm inside of the agent, and I'm watching the endpoints. And if I do kubectl, or I have to do Cilium BPF LB list. Look at that. So there we see basically the plumbing of what we see from the endpoints on this side, right? So we can see that all of the services that are defined for this particular service, which is 10, 110, 126, 220. If I do kubectl get svc-o wide, cool. 10, 126, 116, 220, we can see that there. And the port we're listing on, 8080. So there it is, 10, 110, 126 is 220, 8080, all of those endpoints. And they're all just, part of that endpoint set. So there we go. So now the next thing we want to do is show that if one of these moves to terminating true, that we see it churn from this perspective. We see the change here on the agent, and if we could be looking at any agent, we should be able to see that change in any of them. But in this case, I'm actually looking at the LB list for like the control plane node. So if I do kubectl, actually, let's go ahead and do our watch again. So there we see that watch. We're going to do another little terminal down here at the bottom. And if I would just do a rollout restart of the deployment, then we can see terminating nodes. We can see terminating coming true, and we can see that change. You can see changes happening, but I wonder if there's a way for me to actually present this data so that it's a little bit easier to understand. LB service list. Service list, and then I want to see 4. Hey, all right, so watch. So now I'm actually watching a live version of this, or a snapshotted version, updated every 4 seconds or every 2 seconds. You can see it's pretty darn stable. Nothing's really changing about it, which all makes sense, right? These are the same deployment, and if I do a deployment change, there we go. We can actually see the change happening live on both sides, right? Healthy endpoints, things that are moving to terminating. We can see them coming and going from the node. And while that's pretty neat, I think what would be more valuable in this example is if we're able to see something that's in that time between sigterm and sigkill, and the consideration therein. So let's take a look at that. So the way I'm going to do that, is I'm going to do this. So I have, see, where did I put that? Go 20 okay. Minutes R. Get okay, so I made this Docker file when I was thinking about this particular problem. So let's take a look at the script.sh. And this is just a simple little bash script that's going to run forever. It's going to echo a date every 1 second. And it's also going to echo if it saw a sigterm. And then it's going to trap that sigterm. And you can see that nothing else happens inside the function. And that means that all it's going to do is tell me that it got a sigterm. It's not actually going to terminate. But if it sees a sigkill, it's going to be done, right? And so let's play with this a little bit. Let's enter this into the situation here. So I'm going to go ahead. So I've already built this, and it's called Docker image list grep lion, and I called it what do we call it? I called it sigterm stable. So let's play with this a little bit. So here's what I'm going to do. I'm going to do a kubectl edit deployment echo. Resize the window that I'm doing the editing in because, oh my gosh. Okay. And I'm going to do an image, and we're going to change this to Maui Lion sigterm stable. Okay. And then I'm going to add a command. The reason I have to do this is because I want to make sure that it actually does the thing. Script.sh. So let's just try it without first. Let's see if this actually works. So you should see a bunch of churn here because I'm actually making changes. And we should also see a bunch of endpoints have changed. Simplify our search here and just look for terminating for a moment. Okay, so that means that. So now what I want to see is I'm going to do kubectl tail -- help. I want to see the logs for -l app pods -- show labels app echo. So I want to do kubectl tail -l app equals echo. All right, so now we can see all of that happening. And now if I do one more little window over here, pop that down so we can see our endpoints. And I do my kubectl rollout restart dash echo again. Rollout, okay, rollout status limit echo. Oh, okay. What? Rollout restart limit echo. Hey, okay. So now I saw that. Right, so I got my sig terms. I'm seeing some trues. I'm seeing some changes on this side. Go back to terminating true. I'm going to scale this down. kubectl scale deployment go replicas to it'll get pause. Wait for those to terminate. That is surprising to me. It appears that, as we normally do, we have found some kind of bug. Because I have this in a terminating state, but I'm not seeing them be pulled out quickly. Bum, bum, bum. So let's do Cilium status verbose. Is the feature turned on? No, 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 no. Graceful termination enabled. Yeah, looks like we found a bug. Good times. We are in strict mode. We are seeing the thing is graceful termination is enabled. We are seeing that the service, that's our service, kubectl scale deployment replicas 10 go. As they become ready, they become available. Let's scale it back down to 2. You see, we are seeing the terminating signal. We're not seeing the subsequent service removal. All right. looks like there's a bug here. It's waiting for the entire grace period, which is by default 30 seconds, which is why it takes 30 seconds for this to remove. Boop, there it went. That was 30 seconds. Okay, well, there's a bug. I am going to see about getting that bug fixed, and then I'm going to redo this episode to figure out to show this feature, because that should also be doing things. But there's actually one more thing I wanted to talk about before I go, which is the feature of the host level node graceful deployment stuff. That was actually also kind of a cool feature. So let's go ahead and scale this back up to 10. And then we're going to be able to see kubectl get pods -o wide. You can see that these are dispersed right now across different workers, right? Worker 1, worker 2, worker 3. Let's see, custom columns, like -o custom columns. And then we'll do node spec node name. -o custom columns equals, okay, so there we can see we do sort, and then we do unique -c. You can see that they're dispersed across the nodes, right? We have like 3 on worker 1, 3 on worker 2, and 3 on worker 3. And what's interesting is that there is actually now a functionality inside of Kubernetes that also marks these nodes as terminating in the case of a node drain. So if I were to do kubectl drain worker 03, ignore daemon sets, delete empty dir data, and this is a way of just saying, I want you to drain this node immediately. If I do that, I can see those pods actually start immediately becoming in a terminating state, right? They're still being considered for the load balancer, which is interesting. Actually, I wonder if that's true. What if I did CLB, because maybe what's happening is a different thing, right? So if I do Cilium eBPF LB list, hey, you know what? Let's run that experiment again, because I'm just realizing that I was looking at the service definition, which may be different than the LB implementation in eBPF. So let's do this one more. Let's do this experiment one more time. Hello. Did I freeze? That was weird. Okay. Cilium LB. Nope. Cilium BPF LB list. Watch. So what we're watching for is this 8081 here. Actually, let's just do this. Let's just do 80. Okay, there we go. So now I'm actually only looking at that service. Any updates to it, I will see. They're all not in terminating state. Kubectl scale deployment echo replicas 2. Ho, it works. Okay. So that's where I was missing. There's no bug. It's actually functional. Because what you're seeing here is that the endpoint is still in terminating, and it's still defined as part of the service, but we are not considering it as part of the load balancing. So that was my mistake. Awesome. No bug here. So what's happening here is now we're actually seeing the change that we were expecting to see before, right? And if I were to do scale replicas 10, as they become healthy, we're going to see those endpoints in consideration. They'll be added back to the data path. Yeah. And if I pop it back down to 2 again, boom, instantly. The ones that have moved to terminating have been removed from the load balanced implementation in BPF, right? These endpoints are the only ones still in consideration. The rest of them have been removed. And that basically is the decision-making part. When a new connection comes from an application and goes toward a destination, only these endpoints would be considered. Any existing connections that you have to those pods would continue to work, right? Because we're not actually changing the data path to those pods. We're just making sure that we don't send any traffic to things that are not in consideration when making the load balancing decision. That's pretty cool. Okay, so let's do one more test here. Pop this back up to 30. It'll uncordon for 3. Oh shoot. It'll roll out, restart. Deployment echo. And I want to look at that dispersal again. Okay, I got 10 of them on worker 3. Okay, so now what I was trying to show before was if I go ahead and do my drain, these are the ones that are being knocked out. They were immediately removed. And as they get rescheduled to other nodes, that's where we're seeing the change. We're seeing them added back in. Okay. Nice. Evicting some nodes now. So this is actually the termination of the pod that we were talking about before. So when that pod is marked evicted, that's when the agent is going to see the deletion of the pod, and we're going to remove the rest of the data path. So any existing connections that lived longer than 30 seconds would have been removed. All right. Well, that's what I wanted to show you today. I hope that it was helpful. It was a kind of an interesting scenario and a misunderstanding on my part that the service definition would change. The service definition doesn't change. What changes is the load balancing implementation, right? What changes is that those endpoints, like the service definition still encompasses all of the endpoints that are defined within that service, regardless of whether they're terminating or not. Until those service endpoints are removed, the service definition will show it. The thing I wanted to show you was that the load balancer considers the terminating immediately. As soon as that endpoint goes to a terminating state, we immediately remove it from the load balancer. And so the routing decision that we make as an agent, in eBPF happens immediately. We see that change immediately. So thank you all for tuning in. I hope this was helpful to you. I learned a bunch, and it's always kind of fun to explore new features and new functionality. Sorry about the confusion, and I hope you have the best weekend of your life. And thank you for tuning in. And we'll see you all next time. So take care. Yeah, that was kind of a fun one. Christopher and I are like, we're like this, and it's true. I'm happy it worked out at the end too. It was this stuff is complicated for everyone, honestly, I think. And some of this stuff is like, the set of assumptions that we operate under is sometimes, misleading. So in my case, I was looking at the service because it was an easier way for me to display that data. And then when I was realizing, but the service is actually just the service definition. It's not what the data path is implemented as. That's the eBPF LB command or BPF LB command. So we live and we learn, right? Anyway, thank you. We'll see you all next time. Have a great, great weekend. And boop.